Hey, so welcome to the Pacific Northwest Probability Seminar. We're very happy to welcome back Asaf Nachmias as our first speaker. He was a postdoc here, among other places, and he's now over the border at UBC. And he'll talk about recurrence of planar graph limits.
Thank you. Can everyone hear me? Okay. So thanks for the invitation, and it's nice to be back in Seattle, especially in this beautiful weather. I'm going to tell you a story about recurrence, about planar graphs, and there are going to be circles involved and things like that. So let me just jump ahead. All right. So we're interested in triangulations. Triangulations, they are planar graphs embedded in the plane, such that every face is a triangle. Forgot to mention that this is all joint work with Ori Gurel-Gurevich, sitting right here. Reminding me. So we're interested in choosing one of these objects at random. It could be a triangulation. It could be a quadrangulation, where every face is a square. There are several, of course, technicalities about you have several ways you could define triangulations, but let's ignore all of them and just assume all our graphs are simple. They're all embedded in the plane, and we never care about the homotopy class. We just have an embedding. We don't care if it's we've all seen planar graphs. And we want to choose one in random and see how it looks like from afar. From far away. And I apologize for the pictures. You will see a lot of nice pictures. None of them was made by us. The really childish pictures is the one that we actually were capable of doing, and I put the credit for the pictures, the nice ones like this one. This is a random quadrangulation. Ignore the lines around it. We will get to this later, but of course, we understand that this is a finite space, so we can always draw things at random from here. And we're interested, when n is large, the number of vertices, perhaps the number of faces, perhaps the number of edges. This is all relatively immaterial right now. How does it look like? Here's a picture of how it looks like at a large scale. And here's the credit for this picture. And what you're seeing here is what you get when you rescale you draw a random triangulation on n vertices. It turns out, this is absolutely not a trivial statement, that the typical graph distance between two vertices is n to the 1/4. Okay, this is an interesting fact, but much more exciting is the fact that when you rescale all the distances by n to the -1/4, you have a random metric space. It converges in the usual Gromov-Hausdorff limit to this random compact metric space that turns out to be homeomorphic to the sphere. And this is, a very nice, heavy result by Legal and Mirmont. And there's another way that you could take a limit in this for random triangulations. Instead of scaling the distances, don't scale the distances, and you want to get in your limit an infinite connected graph, right? And this is the kind of the canonical way of doing it, the distributional limit of graphs, which I will now define, that was invented by Benjamini and Schramm. So this is how it works. You have a sequence of finite graphs, Gn. They could be random, but they don't necessarily have to be random. They could be fixed. We will see examples. You choose, this is an important part, you choose a uniformly chose random vertex of this graph. And you look at the ball in graph distance, right here, around this random vertex, and you say that the sequence of graphs Gn converges to, now this is a random rooted graph, so it's a graph and it's an infinite graph and the root. If for every radius r, when you look at the balls of radius r in your finite graph, they converge, right? Assume the degree is bounded, so this is all finite spaces. This converges in distribution to the ball of radius r in your limit. Okay, so this is the important definition of this talk. So let's see a couple of examples, just so we will be in the right mindset. If your finite graphs are a line, just a path of length n, or perhaps a circle of length n, then no problem. It's obviously you choose a random point. It's going to be somewhere in the middle. R is you think about R is fixed and n tending to infinity. So of course what you're going to see around you is just a path of length R. So it converges to just the infinite line. If you start, now here's an example where where Gn is a random graph. You start with the Erdős-Renyi random graph, the complete graph on n vertices, and then you erase each edge with probability 1 minus c over n and retain it with probability c over n. It's a random graph, and you can think about it a little bit, and the truth is that this converges to a Galton-Watson tree, right? Because when you start exploring your neighborhood of length of radius r, right, from a typical point in your Erdős-Renyi graph, you're not going to see any circles. It's definitely going to be a tree, right? And it's going to be a Poisson tree with mean c. You can. Here's another illustrative example. Take a binary tree of level n, of height n, and it converges, well, you would think that it converges to the infinite binary tree, but this is not true. And the reason that this is not true is that we're choosing a vertex at random. And a vertex at random is very likely to be a leaf or a level close to the leaf, level -1, -2. You can figure this out, and you get what's called the canopy tree. And this is a picture of it. We drew this. As you can see right here, this is not the binary tree, right? It has, for instance, it has just one line, infinite line going to infinity, not more than that. All right. Any questions about the definition of a distributional limit? All right, so the first thing that we want to do, since we're talking about random maps, is, we choose one at random. The average degree is constant, is at most 6. Does it have a distributional limit? And the answer turns out to be yes. And this is a very famous paper by Angel and Schramm in the case of triangulation, and by Krikun in the case of quadrangulation. This limit exists. Okay? And it gives you an infinite triangulation or quadrangulation of the plane. Okay? So it's not degenerate. Like you could cook up some examples where everything converges to a point. They called it this uniform infinite planar triangulation or quadrangulation, UIPT or UIPQ. So it's a random infinite triangulation of the plane. This is what we currently know about this. And these, I'm not going to spend a lot of time on this issue, but this is just an issue we expect, so of course we could choose triangulation, quadrangulation. I didn't mention pentagulation or the other, whatever you call the one with 6 edges. And you can continue, but we expect that all of these things behave roughly the same. We don't expect to see in the limit, these small little, petty matters of like what size of faces you chose. And this will also be evident in this work, which I will show you right now. Here's a nice picture by Nicolas Courien of a quadrangulation. And this is a picture I like more because, remember, it emphasizes the point that our graph is always rooted. So we always have a root. We're always sitting on the root and looking towards infinity. So this is why I like this picture. And this, this is a quadrangulation. It has an interesting geometry, right? This is a graph. We can study its graph distance. It's a graph embedded in the plane. We can also study aspects of that, and it has a lot of similarities with Z2. It is one-ended. That means that if you remove any finite set, you only have one infinite component left. So this was proved by Angel and Schramm. the critical percolation probability on it is a half, just like on Z2. This was proved by Angel. It is Liouville. It's okay. We won't. It means that it doesn't exhibit non-trivial harmonic functions that are bounded. This is due to Benjamini and Schramm. This happens also for Z2, Z3, and more. But it is not Z2, this graph. It has all sorts of like bizarre behavior. It has an unbounded degree, for instance. This is this is a fact. It's not immediately clear, but when you draw a random triangulation on n vertices, your maximal degree is going to be of order log n, and you're going to have degrees of all spectrum between log n and a constant. And this is actually a major difficulty. It also has a completely different growth than Z2. The ball of radius r and the graph distance grows like r to the fourth instead of r to the square. This was proved by Angel for the triangulation case and Chasing and Schaefer for the quadrangulation case. And it's a fractal. It's not a nice graph. It's quite crazy. So for instance, the random walk behaves much slower on it. It's strictly subdiffusive, and that's because it has all these like giant dangling ends which don't connect to infinity. It's like a cactus, right? And the random walk, instead of like going in this straight line towards infinity, being very efficient, wastes all his time on the branches of the cactus. And this is a behavior that we see in many examples of, especially of random nature, but also of a deterministic nature, like Sierpinski gasket. I didn't tell you in all of this whether it's recurrent, whether the random walk is recurrent or transient on this graph, and the conjecture, which by Benjamini and Schramm and also Angel and Schramm, is that this graph is recurrent. I don't really have a feeling why they conjecture this. Like, you can cook up examples that all of these things hold, and it's transient. Perhaps Omer would be a better candidate to ask it. But okay. But they did get very close in the sense that if this graph had bounded degrees, you wouldn't be able to solve this problem. And here's a theorem of Benjamini and Schramm in the same paper where they define the concept of a distributional limit of graphs. And they have the following statement. When you have a distributional limit of finite graphs with the two extra assumptions, one is bounded degree, and second is planarity. Right? Very, very important, of course. Then the resulting graph, the limit, right, is almost surely recurrent. Remember, these graphs could be deterministic, but the limit, since the limit, you're always choosing, in your finite graphs, you're choosing a random root, then the limit is a random graph. Right? It doesn't necessarily, so hence, the almost surely should be there even if we're choosing deterministic graphs. I will try to show you a sketch of this proof later. So an example is Z and Z2 that we got, the canopy tree that we also saw. And you really do need, there is no hope of proving that the UIPT is recurrent using this theorem, because this theorem really does require that the bounded degree condition, because, here's a graph similar to the canopy tree. It has weights on it, but you can always, mimic the effects of the random walk is going to walk according to the weights. When it's here, it's going to walk with probability, 2/3 upwards and 1/3 downwards. This graph is transient. Sorry, yes. Sorry? Yes. I got, yes, there's another one, yes. Thank you. This graph you can convince yourself is transient. And it's a weighted graph. We didn't talk about weights at all, I agree. But you can always mimic these weights by having multiple edges. This is an easy thing. And you can convince yourself that, like, with taking a binary tree with these multiple edges, you can get this as a distributional limit. So indeed, the theorem does require the fact that you have bounded degrees. So here's our main result. Instead of bounded degrees, require that the root has an exponential tail, which means that the probability that that the degree of the root, right, the vertex degree of the root, the probability that is bigger than k, decays exponentially in k. So we have that assumption replacing the bounded degree, plus planarity gives you almost sure recurrence. And it's good because we do know these facts, the exponential tail of the degree of the root for the UIPT/UIPQ. This is a result of Angel and Schramm and Benjamini and Schramm. And we really do need this, a comment that I won't explain much about. We really do need the exponential tail. Any tail that is a little fatter, we have an example for that, that is transient. Any questions about the result?
How much more slightly?
Sorry?
How much is it slightly fatter? Can you quantify that in any way, or does anyone know?
So if it decays like e to the minus k to the alpha for any alpha smaller than 1, then there is an example. We could push it more to anything, you know, but it's a necessary thing. So if there are no questions, let me try to tell you a few words about the proof in the little time I have. The proof is we like it. It's cute because it has circle packing in it. So let me give you a brief introduction into circle packing. It is a very interesting theory, and it's very elementary, and it's like easy to get into. So I highly recommend it. There's a really nice paper by Stefan Ori Schramm from circle packing to SLE that is very nice. And here's the basic concept. You have a finite, simple planar graph. I'm giving you an embedding in the plane. Here it is right here. But we're looking for a canonical way of embedding it. What does it mean, canonical? I'm actually not that sure. What is another way that people describe it? This way to represent the graph, it's conformally natural. I read it in your paper, Stefan. I'm still trying to figure out, this. But we have. I can convince you, perhaps that these are correct terms to use. But let's not get into the. There's a lot of connections to conformal maps. But I want to keep this, very simple. But the main theorem that we use is this Kebe-Andreev-Thurston theorem. Kebe discovered it in '36. It was kind of forgotten, and Thurston rediscovered it, and then found out that it was found out there was a corollary of a theorem by Andreev on polyhedras. And it says that any finite simple planar graph can be represented as a tangency graph of a circle packing drawn on the right. So a circle packing is just a bunch of circles in the plane with disjoint interiors. Some of them may be tangent, some of them are not, and we're just drawing them in the plane. And if two of them are tangent, we put an edge between them. This is the tangency graph. And obviously, if you have a bunch of circles satisfying this, and you draw this tangency graph, it's going to be planar. That's easy to see. But the strength of this theorem is the fact that the converse holds. Any simple planar graph you can find a packing of circles in the plane that realizes it. And in fact, when your finite graph is a triangulation, then this drawing is unique up to trivialities and Möbius transformation that keeps circles, sends circles to circles, so nothing really changes. All right, this is the theorem. What does it have to do with probability? Right? This is a geometric theorem. It's nice, but it does have like a lot to do with probability, and this is why it's very fascinating. And we're just starting to discover all sorts of things that Ori Schramm knew, of course, many years ago. But okay, so here's a very nice theorem of He and Schramm. It's a completely there's no randomness in the underlying graph. So if you have this theorem states that if you have an infinite circle packing in the plane, right, such that it covers everything, right? Of course, you can imagine circle packings that don't cover everything, and they're infinite, right? You can, you have, this is the disk, and you put a circle here and a little circle here, and like more and more and more, and they converge to like little points here. and they become smaller and smaller and don't cover the entire plane. And the theorem of Schramm tells you that when it covers the entire plane, it is recurrent. I will show you a proof of this. And in fact, sorry?
What does it mean to cover the entire plane exactly?
So, I knew there was going to be an annoying question here. So it means if you look at the union of all the circles and all the space between them, right, the interstice. Sorry?
Bounded spaces between.
All the bounded space between them, then it covers everything. Okay, so here, an accumulation point, I mean, exactly something. So you don't have like, a sequence of circles converging to a point. That does not happen. And when this happens, your graph is recurrent. And in fact, they also have the converse. When you're in a situation like this, when the graph is packed in a bounded area, it is transient. So you have a dichotomy. This is very nice. Also, bounded degree here is necessary because here's the circle packing of the usual triangular lattice. And now I'm going to change it. I'm going to turn it into, I'm going to rule, I will not have bounded degree here. I want to create a drift to the right. So I'm going to add a bunch of little circles. I hope that you can see them here and here. So whenever you're in a big circle, just because you're performing a simple random walk, you have way more chances of going to the right. And when you're here I put way more, like twice as much circles than I put here, so you still have more chances of going to the right. So here you have, once your random walker travels around here, once he gets to here, he's sucked into infinity. So you do need this bounded degree situation. And let's see how you would prove the Benjamini-Schramm theorem. Let me remind you what it is. Any distributional limit of planar bounded degree graph is almost surely recurrent. Let's go over the Benjamini-Schramm strategy. So Gn is our finite planar graphs. We apply Kebbe's theorem and find a circle packing, whatever circle packing that we want. It doesn't really matter. We are going to normalize it by choosing a random circle. This will also be a random root. Right? So we chose a random circle, and we can always, we have a picture. We can always shrink it. Nothing changes really, and move it around. Same graph. So we're just going to normalize. We'll put the root to be the unit circle at the origin, and we're taking a limit of this thing, right? We have a sequence of graphs. We chose a random root. We drew it in the plane. We took a limit. And now, so what we need to prove here, of course, is what we get is something that covers the entire plane, right? And then we can appeal to the Schramm theorem. And this is absolutely not trivial to show. There's a lemma there. It's short, but it's fascinating. It's really interesting. And the lemma is, it's not that it covers the entire plane. There are situations that you can have an accumulation point, but it's only going to be one. It's going to be an isolated accumulation point. So, of course, I'm not applying immediately Schramm, but one accumulation point, in fact, any isolated set of accumulation point is easy to handle by inversions. I won't go into this, but it's easy. So we apply the Schramm theorem, or perhaps a slightly stronger version of it, which allows some accumulation point, and we get that the graph is recurrent. We use the bounded degree assumption because we use the Schramm theorem. Here's a nice picture by Maxime Krikun of how a random triangulation may look like. Right. Okay, so in order to prove that the UIPT is recurrent, we needed two new ingredients to add to the strategy. One is a quantitative result of the Schramm theorem. The Schramm theorem tells you a graph is recurrent. We're going to study the effective resistance between the origin and balls of radius r in your circle packing, and see how the fact that it's recurrent tells you that this effective resistance, the electrical resistance, grows to infinity. We'll see how fast it does. Oh, I already told you. It grows logarithmically in the radius of your packing. Right? You look at the effective resistance between. We'll go through that. And the second ingredient is to take these UIPT large degrees, right? They are, think about them as stars, and we're going to replace them with a tree. that will have degree 3. And we'll kind of embed it, and we'll need to study how this changes the effective resistance. We'll use the quantitative version of the Schramm. I won't be able to show you the entire thing, but I'm hoping to convince you. I'm not sure about that, but I'm hoping to convince you that it's correct and that you can easily read this. Our paper is short, it's elementary, so I guess I'm considering this talk as a sales pitch. All right, so let's tackle the first ingredient. We have a circle packing of a bounded degree triangulation. Before I tell you how to prove that the effective resistance grows logarithmically in the radius, let me tell you about this important ingredient called important lemma called the ring lemma by Rodin and Sullivan. And it tells you that if you have a circle here in the middle, which is completely surrounded by other circle, as you can see here, then the ratio of the radii is bounded between of any two circles. The inside one and one of its neighbors is bounded from above and below in a number that depends only on the bound you have on the degree. Okay, so this is a very once you think about it, it's relatively easy. Let's say you have circle here and a giant circle here. You'll need to put a lot of little circles here. If this one was in the middle, you need to put a lot of circles here in order to make it completely surrounded. Okay, this is the basic idea. I guess perhaps you could put another large one here, but then you will have a problem. I realize I can see by Russ's smile that I'm giving you a very shady proof of this fact. And okay.
Can't you just have about 4 the same size as the center one?
Well, not if you make this as big as you want. Do you want to come draw it?
If the left circle would be very, very, very small, then the one adjacent to it would also be very small. One adjacent to it would
Why can't
also
they
be very
be
small.
all the others more or less the same size as the central one?
You have a small circle, then one of the two, either to its right or left, is also small. At least one of the two.
Let's
This circle that is blue is not small enough. Try to imagine a circle that is 1 millimeter radius. So,
But what if it has radius 1? The central one has radius 1. That one has radius
so
a billion.
you have-
And all the others have radius about 1. Why can't you have that?
Try to draw it.
yeah, I'm not going to try to draw it.
so let's draw a circle and let's try to draw 2 neighbors to this circle. Both. No. This is not. This is the other direction.
You said bounded above and below.
But then you're going to get lots of circles around the big circle.
Yeah, so
Okay.
right. Yeah, here you would have to have a lot. So yeah, I guess I was wrong actually. Was I wrong? The ratio of the tangent rate. Yeah.
Well, imagine next to
Good,
the big one
okay.
comes a small one and
Yeah.
sneaks into that funnel.
Yeah, the result
Right.
is... the result
What's written here is correct, but I made
not the right
it sound
explanation.
as if like just this picture. But you think about this picture, you have an infinite triangulation if you want, or everything is surrounded. Right? This is not a triangulation because the outer face has more than 3 edges in it. If you want. Okay, let's move on from this point. Here's the lemma that I want to prove to you. The effective resistance, if you have a triangulation of bounded degree, the effective resistance across an annulus of fixed proportion is at least a constant. Here's a picture. Right? So I'm simply looking at the electrical resistance between all the points here in the middle and all the points here outside. And just like you have in Z2, the effective resistance here is at least a constant, and also at most a constant. Why is that? Here's a proof. The effective resistance is, is a minimizing problem, right? You look at all the functions that are 0 on one side and 1 on the other side, like so functions that are going to be 0 here and 1 here. You compute their energy, right? Energy is just the sum over all the edges of the difference square of the function. And you take the infimum of that. That gives you the inverse of the effective resistance. Right? So to show this lemma, I need to exhibit a function that has a finite energy, right? For any circle packing. And this is just going to be a very simple function. It's just going to interpolate between 0 and 1. Right? So on the circle packing. So if this is your annuli, right, and you have a point here, the function is simply going to give the value of this point, simply going to give it the distance from the smaller circle. And this is a Lifshitz function. And let's look at the contribution to an edge to the energy, right? We're looking at fx minus fy square, right? So if this was an edge right here, right, then fx minus fy is simply, is at most the distance between the 2 points, right? This is just a triangle inequality. But now we're coming to the useful fact that we have a circle packing. This is the distance square. Right, here are the 2 circles. Can you see this? Yeah. The distance square, because of the ring lemma, everything, all of the radii here are comparable. The distance square is simply the area of this circle, right? You have bounded degree. You sum over all the edges. So what I'm going to get is approximately a constant of the area of the entire annulus, right? And that is r square. We also had, this is normalized, so the function is 0 here and 1 here, right? So we get exactly the area is 1 over r. We divide by 1 over r square. And this little computation here gives you the result. Any questions about this? It's very simple. And now, of course, to get the sum is bounded, the energy is bounded, so the effective resistance is at least a constant. And what do we get? Of course, that when we have an infinite triangulation, and now, of course, we can, put more and more annuli growing dyadically, and each one we have effective resistance at least a constant. We're using, again, the ring lemma to say that there are no large edges between faraway annuli, and we just add the whole thing up, and we get that it grows logarithmically. In particular, it's recurrent. So this gives you also a simple proof, if you want, of the and Schramm theorem. All right, so in the last 5 minutes, I'm going to try to convince you that this already gives you enough information to be able to control the resistances once you replace the degrees in your random planar map. From when you replace the large degrees, which is a star, you replace them by a tree. So this is what we do. This is really, a fix for this problem. We do it in 2 steps just to be consistent. First, we put, on every edge, we put a vertex in the middle that has degree 2, right here. And then all the vertices marked in black here, they look like a star, and after the first step, and we're going to replace it by a balanced, as balanced as we can, binary tree, right? In such a way that we maintain planarity, right? We can always think about it already embedded in the plane. Instead of this vertex, we put a tree, and we connect it to the previous neighbors that were here before. So we've transformed the graph. Let's call it G star. And, and it's important that this graph has degree at most 3, as you can see by the picture. So, of course, we're ready to, and, another important fact that you can easily convince yourself that if you perform this transformation on the distributional limit on the UIPT, right, you could also perform it on the finite graphs, and you get the same limit. Okay, so there's a continuity issue that is relatively technical. So we know that this graph is recurrent, this G star. But we know more than that. We know a quantitative version of how recurrent it is in a given circle packing. So we also need to, we have that, and we need to relate the effective resistance back to the old graph. And this is the key lemma. And it is the fact that the effective resistance, every time we change, so of course, if you look at the effective resistance, say, if this was your entire graph, the effective resistance between these two vertices is 2, and now it is more than 2. So the effective resistance in the new graph is bigger, right, as you would expect, and it's recurrent, right? So we are losing something here, but we want a quantitative estimate of how much we're losing, and the fact is every time we do such a thing, we're losing a factor of the degree to the effective resistance. Here's here's a precise statement. If we put smaller edge resistances on our new graph, and by how small, we put on this edge, we will put resistance which is 1 over 7, 1 over the degree of the original vertex. Right? So now we decrease the degrees, we decrease the resistance of G star, but we're claiming that the resistance in this new thing, the resistance between big circles, between the origins, say, and big circles remain the same. Okay. So here, this is a statement that I'm not going to prove to you. It's a calculation with resistances in this transformation. It's relatively straightforward. So what we need, the last thing that we need is that in this UIPT or any distributional limit, the degree grows practically logarithmically. What does that? What do I mean by that? Right? Because we take this G star of ours, right? We pack it in the plane, right? And we want to say, so this has bounded degrees. Sorry, let me rephrase. We look at our, say, UIPT, right? We pack it in the plane, and we want to say that so we already know, right, that the degrees, of in the graph distance, right? You look at a ball of radius r in the UIPT in the graph distance, the degree there is at most logarithmic. But we need a different statement. We need a statement that says that once you pack it in the plane and you look at a ball of radius r, the degree there is also at most logarithmic. It's not the same metric. Now we have two vertices, and we're looking at the Euclidean distance between them in the packing versus the metric of the graph distance. All right, so this is so my whole point of this was to say that if you know that, say, in a ball of radius r, the degree is at most logarithmic, when you do this transformation G star, right? On G star, we know by the quantitative version of Schramm that degrees grow logarithmically. If you believe that I've only lost a factor of the degree, then the new resistance in G between, say, the ball at the center and the circle of radius r, the outside of it, is at most log r. Right? Sorry. So it's by the quantitative Schramm, you have here this log r, and you divide by the maximal degree. Right? So the resistance is at least a constant. Of course, we need to prove that the resistance goes to infinity. But the point is that the resistance is at least a constant, not only when you look at the vertex at the center, but from any finite set. The same calculation works. And it's easy to see that if for any finite set the resistance to infinity is at least a constant, that means the resistance that the graph is recurrent. The resistance is actually infinity. This is easy. Thank you for your attention.